So in thinking about the magnetic sun, we're going to start with thinking about where the magnetic field actually comes from. So we may have mentioned in the past the word plasma. Really all you need to know about it is that it's generally hot gases that have so much energy or so much heat that some of the electrons on the atoms have been stripped off. So if we consider a standard picture of an atom, if you apply enough energy to an atom, you can actually pull off electrons from its outer shells. And the more energy you have, the more electrons you can pull off. Now we have this ball of gas. Some of the electrons are loose, they're roaming around free, and then some of the atoms are missing electrons. So that means that our electrons, which have a negative charge, are in one cluster, and we have ions, which is what we call the atoms that have had electrons either removed or added, but in solar physics they're almost always removed. This is what we call a plasma. It's basically a charged gas. And plasmas occur in a lot of different places. So you get a plasma when a lightning strike hits the earth. The lightning actually electrifies and charges the air that it travels through, and it generates a plasma. The sun is not a solid body. It rotates at different speeds depending on how far away you are from the equator. The equator rotates the fastest, and then by the time you get up to the north and south poles, that's rotating much, much slower. You have electrons that are traveling around in a circle, and when you have a circuit or a circle of electrons, what is that? That is an electrical circuit. And whenever you have an electrical circuit, you also have a magnetic field. So last week we mentioned the tachocline, that weird boundary layer between the radiative zone and the convective zone, where the sun stops rotating all at the same speed in the core of the sun and starts rotating with this sort of fluid effect in the outer layers of the sun. And we think that the tachocline is also where the magnetic field is generated, where this circuit is flowing. But how does it actually get to the surface of the sun when it's generated under the photosphere, inside in the invisible part of the sun? Well, this all ties back into the fact that the sun rotates differentially. So like we said a few minutes ago, it rotates faster at the equator than it does at the poles. And so what happens is the magnetic field that's being generated is tied into the plasma. They're all connected. They can't pass through each other. And so as the plasma rotates with the rotation rate of the sun, it drags the magnetic field with it. What happens is it actually gets wound up and wound up and wound up in this region above and below the equator. You start to get these areas of dense magnetic field just above and just below the equator of the sun. Now this is still underneath the surface of the sun. We can't see this just yet. So as this wrapping effect happens, eventually there's so much magnetic field, it becomes magnetically buoyant, and it actually starts to rise up and burst through the surface of the sun. And this is what we see as sunspots. So the area where these magnetic fields start to rise up and they come through the photosphere, the area where the magnetic fields are actually connected into the surface, are what we see as sunspots. So it's not so much that there's no material there, it's just that the surface of the sun has been pushed aside. The plasmas on the photosphere have been pushed aside so as the magnetic fields can rise up and protrude out through the surface of the sun.